as sheaves of vertex algebra and stringy manifold invariants. Please.
Thank you. So let's just count the hour, otherwise I'm going to go. So of course, thank you very much, guys, for inviting me. Having 3 weeks in Florence is an incredible experience, but having wine at Galileo's house is just, how this master guy said it, is priceless. All right, so a couple of warnings, I guess. I've done this a couple of times already in Nordita, now here, and I'm not going to change what I'm saying. I'm just going to change the way I'm saying it. And please don't take this the wrong way. Please don't take this the wrong way, but I see many old faces here. I prepared this so that I'm hoping that most of you will be very bored. So if you're a student and you're starting doing computations that want to look something like this, and you just started doing these kind of things, then you might gain something. Otherwise, you might already know everything that I would say in these talks. And hopefully, half of you will be very bored in the first talk at least. So I'll set up why is that I'm here to tell you something that is very, very basic in the first talk at the very least. So let's start with this square. This square, I assume that you know better than me. So I'll have the classical word in this picture, and the quantum word in this side. But for me, this will mean the following. I mean, of course, I'm not going to attempt to say anything physical in these 3 lectures. But for me, this will mean the following. Here I'll have Poisson algebras. And here I'll have associative algebras. Well, this you may know very well, but here is what I want to explain. These are Poisson vertex algebras. And here I'll just have the formations of those which are vertex algebras. And I want to say a few words about what these Poisson vertex algebras are and how do they relate to geometry, in as much as Poisson algebras relate to some geometries as well. Okay, so last week we've heard grandiose talks about that part of the word doesn't exist, that part of the word not existing. The only thing that exists is the quantum word, and somehow we can look at families of these guys and look at their limits and define these guys. So I'll define functors in these directions that are called, I'm going to call classical limits. I'm not sure how people call this in the physical world. So here I'm going to think of finite dimensions or finite dimensional manifolds. In the bottom side of this board. And then in the top side, I'll think of loop spaces. I'm not sure how these functors are called typically. I'll call them zoo. Like looking at the center of mass of the string. But anyhow, let's start. So there are 3 objectives that I want to do. I want to first sell you something. So I want to claim the following. So computations are simplified. By a formalism that is called lambda brackets. But this is nothing that you don't already know. If you know how to make computations along this line, you've already used this thing. And I'm going to tell you how to write down, to pack OPEs that you already know how to compute, and they're going to be exactly the same computations you do. And it's not going to be much different what I'm going to write. So the language might be somehow a steep learning curve, but it's really writing down the same computations you guys are doing. It's just that once you get used to using this tool, it's easy to make computations. Still, today I can tell anyone that has done computations of this form, you know that if you go to higher order polynomials on these guys, the singularities that appear there are much harder. And if you want to do this at every order, you need to do this for every order polynomial. Or you might even want to do this for smooth functions on these observables. And then the singularities get really nasty. So I'll give you a tool to perhaps compute those kind of things. The second thing I want to tell you is a notion that might be a little bit foreign to physicists, that is how to glue field theories. So the typical way you define a field theory is as Richard is doing. You have a global theory. You just pick an auxiliary manifold in the sigma model, for example, M, and you write down a global action. And then you can describe these things. So typically, you describe things locally. In physics, the description is local. You choose coordinates. But the action is a global thing, and you started from a global object. What I wanted to tell you is that there's other ways of constructing theories which are local in nature. You define the whole theory, the theory locally on the target manifold, and then as a free field. And then interactions appear when you start gluing on patches. So the gluing procedure produces interactions. But of course I'm going to be talking about mathematics, I'm not going to talk about physics, but gluing produces interactions. And perhaps the interesting part of the story for me is to try to translate from this gluing field, the theories that are constructed by gluing, to the actual theories that you work with. And in this interaction between these two theories, these two forms of presenting the theory, there's nice mathematics or physics to be done. The third part that I want to tell you, I scaled this back quite a bit. Instead of talking about stringy manifold invariants, I just want to tell you about one thing, which is the elliptic, probably two variable, elliptic genus. This is going to be the third talk, and I'll tell you how you obtain this from a particular vertex algebra that is down there in that corner, which is called the chiral ram. So this is chiral, the ram complex of a manifold, and how the structure of vertex operator algebra of that guy might help you to prove interesting theorems. All right, so let's start. But just to set the tone, I don't know if Nick is here, but he might complain. So I'm going to use a language that most people here use differently, and in the derived word is the right tool perhaps to look at these things. But I'm going to be very, very pedestrian, and I'm going to be talking about vector spaces. So when I say K mod, this means just a vector space, and it's what it was hyped in mid-stop. Nothing is going to be derived. So let's say P is a vector space. Oh, by the way, yeah. I'm sorry, I used to write K, but here I mean this. Or R, if you want to write it here. So P, definition, just to set the tone that this is going to be for students. A Poisson manifold, a Poisson algebra is one operation, which is a commutative unital algebra. We have another operation, which is a Lie bracket. I'll write this with braces. Lie algebra. And we have the Leibniz rule, which is just simply that A, B, C is equal to A, B, C plus B, A, C. So I'll work with graded things. So that's a Poisson algebra, and you may ask yourself, suppose I give you a gradient guy. So let's fix the gradients. I'll always have my commutative, so I'll assume that all my algebraic objects are going to be graded in the following way, and I'll pick the product to be of degree 0. So this means that Pi times Pj lives inside of Pi plus j. And all my Lie brackets will be of degree -1. So Pi, Pj will live inside of I plus j minus 1. So if I have that structure, I'll call that a graded Poisson algebra. And the question we may ask is, what is a Poisson algebra generated, or freely generated, or truncated, I guess is probably the better question. Is 0, and 1. So if I give you a positive, yes?
Just one question. When you say community for various things, are there signs?
No, there's nothing fancy. There will be later, but I don't want to do anything fancy. Vector spaces, you know, the category is very simple. Alright, so, yeah, okay. So, what is such a Poisson algebra in degree 0 and 1? Okay? Well, the structure quickly tells us what it is. So, P0 is a commutative value. Right? We don't have any bracket there because the bracket is degree -1 is empty here. This is 0 vector space. So we only have a commutative algebra. Let me denote that algebra this way. Okay? So P1, again the multiplication gives it the structure of an OX module. It's a module over that commutative algebra. The multiplication was associative, and something in P0 times something in P1 lives inside of P1. So this gives it a module structure. I'll call this module A. Alright, so the bracket, well no, let's restrict the bracket to P1. So this bracket produces to me a map, a bilinear map to P1, which is a Lie bracket. I'm calling A now P1. Which is a Lie bracket. But just to make sure, instead of talking about bilinear guys here, let's take the tensor product over K. This is a linear. It's bilinear over K. Just to make it explicit that this guy is not bilinear over O, it's bilinear over K. And finally, the bracket also, between something in P1 and something in P0, gives me an action of A acts on O. But just the brackets. If you have something in A and some F here, then I can call the bracket A of F, I'll just define it to be this. So this is an action of A on F. The Leibniz rule says that this is, the Leibniz rule, by taking something in P1 and a product of two things in P0, says that this action is by derivations. So this is A of Fg is equal to AFG plus FAG. And the final piece of information we need to use is the Leibniz rule again, between something in P1, something in P0 times something in P1. So this is a relation between the Lie bracket in A and the O module structure in A. So from the Leibniz rule, it follows, so this Lie bracket, let me write it, like this. From the Leibniz rule, it follows that A bracket with FB is equal to the action of A on F times B plus F times the bracket of A. So for those of you who are differential geometers, that you won't like this observation, but what is a Poisson algebra generated in degree 0 and 1 is a Lie algebra. Some people might want to have, to call this a Lie algebra, you would want to have this guy to be actually, have some local structure. So this X should be some topological space, and this should be the ring of functions on that topological space, or the sheaf of functions in that topological space. And then this A, you may want it to have locally free of finite rank. I don't care about those things. But this is the notion of a Lie algebra. You can think of this as functions on a space, this as a vector bundle, these are sections of a vector bundle, with a Lie algebra structure and an action on functions. Examples of such things, and I only care about one example because otherwise I'm not going to get to the infinite dimensional setting, but example is, let's look at X a manifold, Tx its tangent bundle, So vector fields. Of course, OX to be functions, smooth functions. I like better holomorphic manifolds and O to be holomorphic functions. And then Tx is what I would call A. And the bracket is the Lie bracket of vector fields, and the action of vector fields of functions is by derivations. So this is an example of a Lie algebroid. So this is a Lie algebroid, the tangent Lie algebroid. And what is the algebra freely generated by this guy? The Poisson algebra freely generated by this guy is the symmetric algebra on Tx, which is the algebra of functions on the Poisson manifold T star of x. It's a symplectic manifold, it has a Poisson bracket, and that's it. Alright, so this is my only example. I guess I can give you example 2, just to contrast with the next case.
That P is by P0 plus
No, P is the whole Poisson algebra. And if you look at the degree 0 part, it's OX.
Okay.
So the degree is written there. The degree 0 part is OX, the degree 1 is Tx. Alright, so the example 2 is this example. Is example 1. Oops, not the tangent. No. Example 2 is when the OX is just K. So when OX is just K, there's no derivation to be fiddling around. So essentially all of these structures degenerate, and the only thing that I'm left with is this Lie bracket. So A equal to G is just a Lie algebra. So Lie algebroids are just sort of Lie algebras living on manifolds. So when the manifold is a point, a Lie algebroid over OX is just a Lie algebra. Alright, so that's as much as I want to say about Poisson algebras. And I hope Poisson algebras in degree 0 and 1 became clear. Because the next step is going to be going to infinite dimensions, and this might be slightly confusing. Bear with me just a second. And I want to describe what Poisson vertex algebras are now. And in order to describe what Poisson vertex algebras are, I need to tell you what Lie algebras are. So I'm going to replace what the Lie bracket is. A Poisson vertex algebra will be the same thing, will be a commutative algebra with Leibniz rule, but the Lie bracket will be different. So I want to replace what a Lie algebra is here by the loop algebra of G here. So I want to replace manifolds X by the loop space of X. And the way I think of the loop space of X is by replacing K modules by K del modules. Where this guy here is this is just vector spaces with one endomorphism, nothing else, no more requirements. So I'm thinking of this del as the derivative along the coordinate on S1. So this sigma is going to be a coordinate on S1. This is the way I'm thinking on the loop space, just that whenever I see a vector space, I should have a K of that module. And these loops are not going to play any role in our lectures. But the question is, how do I define a Lie algebra on vector spaces with an endomorphism? So exercise number 1 is, oh, by the way, I have some lecture notes. The lecture notes are much drier than what I'm saying here, but they're online. Oh, I think they're online already on my site, and if they are not, they're going to be tonight. So this exercise should be there, which is the following. If you come up with a naive definition of what a Lie algebra is, so Lie algebras on K del mod are the same thing, are Lie algebras with a derivation, are Lie algebras G with a map, which is a derivation. Let me tell you what I mean by this exercise. What is the usual, so let's not write this. What is the usual definition of a Lie algebra? It's a vector space G with a bilinear map from G tensor G, or a linear map from G tensor G into G, which satisfies Q symmetry and the Jacobi identity. The key thing there is the tensor product, is G tensor G. The category of K modules has a tensor product. If you give me two modules where del acts, on the tensor product of vector spaces, del also acts. And it acts as, in one factor, plus the action of the second factor. In that category, if you write the usual skew symmetry and Jacobi identities, you will find this notion of Lie algebra. And I don't want to use that notion of Lie algebra. I don't want to have Lie algebras with a derivation. I want to do a fancier version of what a Lie algebra is in this category. So the exercise 1 is the following. In the naive notion of a Lie algebra in this category of vector spaces with an endomorphism, you will find this notion. This is not the notion I want. The notion I want is the following. The notion I want is, let's start with G, a module with an endomorphism. Then I can take G tensor over K with G. And instead of looking at this guy as a K of del module, I'm going to look at this guy as a K of del 1, del 2 module. Namely, del 1 acts on the first factor as del, and del 2 acts on the second factor as del. And I have G. This guy is a K of del module. So I want to make it into a K of del 1, del 2 module. So this is going to live again in K of del 1, del 2 modules. And I'm defining something that I will denote this way. And it's as simple as this. K of del acts there, and K of del acts on this polynomial ring. Del acts here, so I need only to tell you how it acts here. And it acts by del 1 plus del 2. You might want to have a minus there. That's essentially the idea. And now, on this side, I have an action of del 1 and del 2, which is by multiplication 2. So now I can look at my Lie bracket living here. So now this is going to be a morphism of commuting with the action of del 1 and del 2. And this will be my definition of a Lie algebra, of where the Lie bracket lives. Don't worry if this is daunting. This soon is going to be clear. I'm going to write down explicitly actions. But the idea is very simple. Typically, when you want to define a Lie algebra, what you do, instead of looking at math from something that lives, so we have our G living in a space, the spectrum of K in our case. So you have a G living in a space. So typically what you do, you take G times G living in X plus X, and you pull this guy back via the diagonal to again a G tensor G on X. And then you look at a map from that guy into G. Now I'm doing the opposite. I'm looking at something that lives on the product of the two spaces, and I'm mapping it to the push forward along the diagonal of G. If those words don't mean much, don't worry, we're going to write down explicitly these attributes. So I need to tell you what is Q symmetry and Jacobi. And to doing this, since I like vector spaces and explicit computations, I'll replace this guy. Notice that you can trade. So here's the vector spaces. I can trade any del 2 here, passing it via delta to a del acting on G. So as vector spaces, this space there only has K of del 1 tensor with G. Any del 2 that was here, I just passed it acting as del on G. So as vector spaces, this space is what? Is a polynomials in one variable with coefficients in G. And just to not make confusion with this del 1 being there, since I'm already talking about vector spaces, I'll call this del 1 just lambda. The back row of this is that I just broke the symmetry on what was 1 and 2. Okay, so definition. If you like geometry though, so giving a talk about this and not giving this reference is stupid. The right language for this is Beilinson, Drinfeld, Algebras book, And this is what is going to be called the D star algebra. With that one. Okay. But now I'm going to give the description just in terms of vector spaces, and we're going to give examples, explicit examples. So definition, A, Lie conformal algebra, so now this is Katz's notation, algebra, is a K of del module G. So I'm keeping the del acting on G, and I'm going to keep the lambda to be this del 1. So I made the difference between the del that I was left here and the del that was acting on G. So it's a K of del module G with a bilinear map. So it goes from G tensor G, what is written there, into polynomials in lambda with coefficients in G. So this sends A, B to A lambda B, which is just simply the sum of lambda to the n Cn, finite sum, and Cn lives in G. Satisfying three actions. One. Well, so I have some actions that were remainder of the fact that this morphism should have commuted with the derivations on both sides. So those actions, let's write them down. Del A lambda B is minus lambda AB. And del is derivation. So plus del is a derivation, so this is del of A lambda B is just simply del A lambda B plus A lambda del B. The only thing that is very unfortunate, this lambda bracket that I'm writing here is exactly what you call OPE, and it's unfortunate that it's not apparent now, but hopefully it's going to be apparent tomorrow. But this lambda bracket that I'm writing here is really just exactly what you guys call OPE, or the singular part of the operator product expansion. 2. So this is as much as the differentiability on these two sides gave. Now skew symmetry and the Jacobi identity. So these are hard, but we're going to check this in examples. So A, B lambda A, I would like to write here a minus A lambda B, but that's not true. And you can see it here already. When I flip these two guys, and I flip these two guys, del 1 and del 2 are changed. And here I broke this symmetry. This cannot be skew symmetric. I chose 1 del 2 is the one that I passed here, and del 1 is the one that I kept. So this can certainly not be symmetric, skew symmetric. So what happens here is, you do this. So this means the following. Compute A lambda B. You're going to get some power series in lambda to the n, c to the n. Replace lambda by minus lambda minus del, and apply del to Cn. You get a polynomial in G with coefficients in lambda, and these two things are equal. We're going to check this explicitly in a second. And the Jacobi condition is similar. Plus Jacobi. The Jacobi condition says, now I need to be careful, and this is going to appear in geometry in a second. When your bracket is not skew symmetric, Jacobi you can write it in many ways. So Jacobi you can write it as A bracket B bracket C plus cyclic permutation is equal to 0. But and the fact that this is equal to this, which is the Leibniz rule for the adjoint action of A. So let me write it with commas first. So the typical Jacobi condition on Lie algebra is this. AC. The fact that this is the same as the other Jacobi condition of writing A bracket B bracket C and taking plus cyclic permutations equal to 0 is using the fact that the bracket was skew symmetric. So here we have a choice. How do we write Jacobi? And I chose this. I chose the Leibniz condition because our bracket is not skew symmetric. These are actually going to be different. And I'm going to write A lambda mu lambda C, A mu C, mu lambda C. That's wrong. That would be the naive replacement for the Jacobi condition. And this fails. I need to put here a plus lambda. And we're going to check this in a second while. But these are just, both sides are polynomials in two variables, lambda and mu, with coefficients in G. And coefficient by coefficient, they should be equal. So this is my notion of a Lie algebra. If you accept me this, the rest is yes.
Is this possible to recover the simple notion of Poisson algebra from this?
Thank you. Yes. Yes. That's a great question. So let me give you, since I haven't started with Poisson, let me give you the recovering of the Lie algebra condition. Okay? Notice this. Notice that if I put del and lambda is equal to 0, so that's the observation. So observation, del is equal to lambda is equal to 0. Lambda is also a del in this geometric picture. So this is the same thing as putting all the dels to be 0, which was in my loop version, putting the derivative with respect to sigma is equal to 0. So it's meaning that I'm looking at loops that are constant. This should be a Lie algebra. And this is in fact a Lie algebra. Is a Lie algebra. What does this mean? If I put lambda and del is equal to 0 here, well, here I just get 0 is equal to 0 on both sides. So this actually disappears. But here, I don't care what del, so the only term that doesn't vanish here is the constant term in lambda. And I get that the bracket is Q-symmetric. And here, the only term that survives is the constant terms in lambda and mu. And I get that the bracket satisfies Jacob.
But I think the question was slightly different. I mean, because when physicists say Poisson, you mean, Poisson brackets on the loop space, right?
I'll get to that later, but I'm talking only about Lie algebras here, and I don't have the product. I can't answer anything about Poissons because I didn't put the product yet. But I want to give you first how you get a Lie algebra, and then how you get a Poisson algebra in the usual case. So this would give you, and Maxim's question I'll only be able to answer probably tomorrow. But this says that G divided by del G divided by del G with the bracket, the usual lambda bracket, when lambda is equal to 0, so we define this to be the new bracket. This is the Lie algebra. And this is actually going to be one way. If you kill derivatives, you get the usual Lie algebra. And it's sort of like in the spirit of Maxim's question. Typically, when you in physics do computations of the loop space, you don't write the Poisson brackets on the actual functions of the loop space. You write expressions that are of this form. I don't want to get there, but you write expressions that are of this form. You always integrate over your loop. What does it mean to integrate over your loop? This is this operation. Killing derivatives is integrating out. So I'm thinking on passing by the quotient by derivatives is the same thing as integrating out. Because you actually, to check that your Poisson bracket is a Poisson bracket, you integrate by parts.
But still, why you don't want to make a comment at this point for physicists? That what you are doing, you're just doing some type of Fourier transform on the loop space.
I don't want to do this because
physicists don't understand.
I refuse to do this until I give examples and until I get to tomorrow. I refuse to do this. I think that's the wrong way of thinking on this problem, and when I connect with operators, I'll make this observation. Yeah.
So, can one write these three axioms in a more easy way using the original bracket?
Using
before this symmetry break?
Yes. Yes. The right answer is the following. So the right answer is as follows. The category of K of del modules, if you wish, has a structure that is not really a tensor, so it has a tensor structure, but it has also another structure, which is the structure of a colored operator. And in a colored operator, so it has something very difficult called a pseudo-tensor structure. And in a colored operator, you can define a notion of a Lie algebra. So a Lie algebra, in that category, is this object. So in some sense, I don't need to write the actions in any other different way. It's just the Lie algebra object. I can tell you details later, but yes. Alright, so, no, I'll do this your observation.
No, but I think it's important for some people because you don't understand, they don't understand what you are doing.
That's fine, I'll give examples now, but to answer that question I need to go to the loop space and I need to write a coordinate sigma that I
refuse to. You can make a simple comment that, secretly, let me make a comment on your behalf. Secretly what he's doing what physicists will do, Poisson brackets on the loop space, you do Fourier transform, and lambda is a formal parameter which keeps track of the calculations which physicists is doing, right?
That's right.
You like to do this way, physicists like to calculate.
That's absolutely correct, but in order to make this statement precise, I need
no,
to
but I'm not
get
about precising, I'm just about relating what people know, right?
Alright, so let's give one example that you do know, the Virasoro example. So this is going to start to look like an OP that you know. So this is an algebra that is generated by one guy. So this is as a module. It has one basis element L plus a center. So if I want to go, I'm not going to be A. So this C is killed by del. It's not a free module. C is killed by del. Del of C is equal to 0. C is central, and the bracket is as follows: L lambda L. That encodes all the commutation relations of the Virasoro-Lie algebra that you know. But since I am refusing explicitly to connect to operators, let me just check skew symmetry here. But notice that when you write down the OPE, for those of you who wrote the OPE of the Virasoro, what you find is a derivative plus your Virasoro field times a derivative of the delta function plus a third derivative of the delta function. So this lambda, what is encoding in Maxim's comment, is the derivative of the delta functions that appear. And this del, what is encoding, is derivation of the fields. Okay, so let's check skew symmetry here. Skew symmetry should tell me that this is equal. If I flip these two guys, I should put a minus and replace lambda by minus lambda minus del. So I should have del, well, minus 2 lambda minus 2 del L plus. And here I should put minus lambda minus del cube. Oops, minus lambda minus del cube over 12 times C. Let's go on. So you see, this procedure of not making it skew symmetric actually restores skew symmetry. So I have a minus with minus the 2 lambda, and then I have a minus del with a minus here as a del. L plus, and this guy killed C. So I'm only left with minus lambda cube, which is what I wanted to do. So it's skew symmetry, which is apparently something which wasn't symmetric. And for those of you who know what a current algebra is, this should already tell you, oh, yes, the Dorfman bracket is appearing somewhere. Okay, exercise 2, check Jacobi. Do it. Do it is an easy exercise and it's an interesting exercise. This thing for a physics student in the first year takes some time. Whether here is triggered, and you'll understand why the co-cycle of the central extension of Virasoro is of this form. Check Jacobi. I'll give you another example where I'll check Jacobi now, which is the second example is the affine Katsuni algebra. So this is something simpler of that form. So let's say G is, so I'll call this curve G, to be consistent with my notes. So it's going to be generated by guys in G. Oh, it's no on the plane here. I defined you the bracket in terms of L and L. C with L commute, C with C commute. And then the statement is that you can extend this to higher derivations of del by using the actions. Whenever I have a del here, I pick it up as a lambda outside. So you can extend it to the whole algebra. The same thing here. So let's go with K times a center. So let's say G is here a finite dimension Lie algebra. G is a finite dimensional Lie algebra, and this guy is a bilinear map, any bilinear map. I want to get this. I want to be forced of doing this. When you check Jacobi there, well, no, I want to get it. All right, so let me give you the brackets. For A, so I'm going to take generators A and B and G. This is the finite dimensional Lie algebra. I'll define you the OPEs of these two guys to be the usual bracket plus, remember, for free bosons you have a derivative of the delta function. So, lambda times the pairing of A and B times the center. And K central, K commutes with everything. So let's check now. I'm not going to check, oh no, yes, I want to check skew-symmetry, but I want to write it. I'm not going to write it. When you do skew-symmetry here, you pick up a minus sign here, that's fine because the bracket is skew-symmetric on the Lie algebra. But the problem is here. You pick up a plus lambda plus del. Okay? So lambda term of that guy should be equal to the lambda term of this guy. So lambda BA should be equal to lambda AB. So this guy has to be symmetric. So let's forget about this and let's take this in sim 2 of G star. It should be a symmetric pair because otherwise Q symmetry is not satisfied. So let's check Jacobi. I can write it. Oh, I have Jacobi here. That's great. Okay, so let's check Jacobi. What does Jacobi tell me? Let's compute this. I have A lambda. Well, I need B mu C. B mu C consists of two terms, B comma C, plus another term, which I don't care because it's central. So it's going to be killed by this bracket. This side here is equal to A comma BC plus lambda times the pairing of A with BC. Just this is the definition that I wrote there. So let's look at the other side. This should be equal, it should be equal to A comma B mu plus lambda C. Again, the lambda term here is irrelevant because it's central. When I commute it with C, it's going to be 0. Plus B mu A comma C. So let's write both of those terms here. The first term is ABC plus mu plus lambda. Remember, this was not making the naive Jacobi here. I added this plus lambda of the pairing between AB and C plus, well, this term here is B comma AC plus mu times B AC. Did I get that something wrong?
You just focus on K.
Oh, K, thanks. Yeah. All this is central. Thank you. Alright, so let's start killing things. The usual Jacobi condition for the Lie algebra just tells me that this is equal to this plus this. And now I need to check at the level of each polynomial. So I have a coefficient of lambda here, and I have only one coefficient of lambda there. So this equals to this is if and only if the form is invariant. So this is the notion of an invariant form for a Lie algebra. That this guy here is equal to this guy here. So this should live in invariant forms. Yes? Is that a question?
No.
Okay. And the second term, well, I killed this lambda with this lambda, but now I'm left with this mu. But this mu is minus, this guy here is minus this guy here, using the invariance of forming. So this doesn't give me any extra condition. Okay, so Jacobi imposed this, and this is essentially saying that the Kac-Moody, so this conformal algebra is going to be related to the usual Kac-Moody algebra. And this is why the central extension for the usual Kac-Moody infinite dimensional Lie algebra are related with those cocycles there, invariant bilinear forms which are symmetric. Okay? So, in some sense, these conformal Lie algebras are ways of using finite dimensional tools to dealing with infinite dimensional Lie algebras. And most of the computations that you do, well, this is going to be a meta-mathematical theorem, but most of the computations that I do at least, when I work with loop spaces, the oscillations of the loops are the trivial part. The hard part is actually the loop. So in some sense you encode everything in these higher derivations. That's a mathematical statement. Alright, so now that I told you, so I want to go back to geometry, something that we know and love better than this. If you accept and if you digest what this notion of Lie conformal algebras are, I can tell you what a Poisson algebra is and go back to geometry. So definition, a Poisson vertex algebra I'm going to have just that. A Poisson vertex algebra is, well, the data is always the same thing. It's a K of del modulo P. 1. This has an operation that is a commutative unit of algebra. Del should be a derivation. Del of AB is equal to del A B plus A del B. You're laughing, Demian. What did I do wrong?
No, nothing. I was just thinking, it's not going to be a Poisson algebra in any category.
Well, you should ask Nick this question. If you derive this statement, this is the same thing as Poisson factorization. No, actually at the classical level it is. At the classical level, a Poisson algebra is a Poisson algebra in the compound tensor category of D modules on a curve.
Oh, but it sounds like this commutative product is correct for the usual tensor product.
Yes, so a compound tensor category is this. It's two tensor products that are.
Okay.
This is a commutative one for the Schrick product. Comments aside, this is just a commutative value on vector space. Usual commutative value. 2. The bracket. Ali. So I'll write the brackets now with braces to remind of the previous thing. So this is a Lie conformal algebra. And now I need to tell you what Leibniz is. Leibniz is a trivial one, which is A lambda bc is equal to A lambda b times c plus b A lambda c. So the usual Leibniz. And that's a Poisson vertex. So I didn't change anything. I only changed what the notion of Lie algebra was. But okay, so now I can go back to the finite dimensional world. Before doing so, let me answer your question at the Poisson level. Notice that Leibniz is still satisfied if I put lambda is equal to 0. This is just the usual Leibniz. And I knew that if I put lambda is equal to 0 and del is equal to 0 here, I get a usual Lie algebra. And if I put del is equal to 0 here, well, I'm just getting an ideal. So, P divided by del P is a usual Poisson algebra. And this is my functor. Oops, no one is complaining here. Now I'm killing an ideal. I need to kill this ideal. It is also true that P divided by del P is a Poisson algebra. But that's a deeper statement. So this is what Maxim calls the Poisson algebra on the loop space. When you kill derivatives. So this is Maxim's Poisson algebra.
No, it's not mine.
But this is an actual Poisson algebra in finite dimensions. And I'll give examples of this when I complete the square tomorrow. I want to give. But the thing is that this is my functor that went on the corner of that square that I started. From classical field theories to classical mechanics. From a Poisson vertex algebra to a Poisson algebra.
So when you go from P to dP, it's the same as going to zero modes when you have expansion. And I'm talking.
No, that's not correct. No, this is really just killing this integrator. It's not. No, this is not correct, Maxim.
So can you explain the difference between?
Yeah. So this is a much larger space. This is killing the ideal inside of. I have this Poisson. This is typically an infinite dimensional vector space. If you kill only this subspace here, this may not be a commutative algebra. I need to kill by an ideal to get an algebra again. So I'm killing by the ideal generated by this.
What is killed in which case?
Sorry?
Can you state explicitly what is killed in each of these cases?
What is hit?
What is killed?
Killed. In this case, I am killing everything that is of the form del of A, where A is in B. And in this case, I'm killing everything that is of the form A times del of A, where, B times del of A, where B and A lives in B. In particular, if I put B is equal to 1, I am killing all of this. So this space is typically much, much smaller than this space. I'll give examples of this tomorrow when I actually do this for the whole quantum level.
I think on the bottom you're doing total derivative, so you're doing this
integral by S1, exactly.
And if you do 2 product of integral over S1, no way that it will always be an integral over S1.
Exactly. So this is what this is called local functionals on S1. So this is what physicists do when they actually write down these integrals of S1 and they compute possibilities of local functions.
I mean, physicists call local functional what you call local functional, but then sometimes if you don't put test function, then that's what you're keeping.
That's fine. The test functions are P, and the local functionals are P divided by del. This is also notation of integral system. These are the local functions. Alright, so, but I don't want to get to modes. My claim is that you need to work with finite dimensional tools. This lambda bracket allowed me to work with finite dimensional objects. To describe the Tirasova, I needed only one guy. To describe the alpha and Katsuni algebra, I needed only the finite dimensional G.
But how can this be a Poisson algebra?
No, this is not a Poisson. This is a Poisson algebra. Okay. This is certainly not.
You wrote Poisson, sorry.
Well, that's why they vote. This is what physicists call Poisson when they write this Poisson bracket under an integral symbol. The Poisson bracket that they write on the loop space, T star of the loop space, is not really a Poisson bracket. It's only under an integral symbol that you have this Poisson bracket. It's only when you kill total derivatives. So if I want to make a formal statement, this is an actual Poisson algebra and this is not. This is only at the local level. Okay, so this is what a physicist Poisson algebra. That's a mathematician's Poisson algebra.
Is it a Lie algebra?
This is a Lie algebra might be. A Lie algebra might be an infinite dimensional Lie algebra. It's a Leibniz algebra for sure. Alright. Okay, so that's right. So it's a Leibniz algebra. I need to think about the decomposition. Alright, so, but I want to get to geometry. I have only 6 minutes. So I can ask the very same question, but I need to put grading. So I'll ask the same question that I started the lecture today. What is a Poisson algebra in generators degree 0 and 1? And this should be some geometrical object that we all know and love. So, for this I'll put the grading. Again, Pi Pj is in Pi plus j, the usual product. The derivative of Pi should be in Pj I plus 1, so I'll declare it to be of degree 1 plus 1. By the way, these gradings are what you typically would call dimensional or conformal weight. And I'll declare Pi lambda Pj. I don't need this, but I'll do this anyways. So if you write something, so let's take A lambda B, this in Pi, this in Pj. I'll put lambda to be of degree 1. So this is the sum of lambda to the n Cn. I will ask Cn to live in Pi plus j. I want this lambda to be of degree 1, so minus n, and I want the whole operation to have degree minus 1. So this is going to be a graded Poisson algebra, a graded Poisson vertex algebra. So question, what is such a guy in degree 0? And this is the geometrical object that we're going to be quantizing in the next lecture. So question, let P be freely generated in degrees 0 and 1. What do I obtain? P0, there's nothing to do. The bracket is obviously 0. So P0 is just a commutative algebra. P1, there's nothing to do. The product is associative and commutative, and associative is the only thing I need, is an OX module. Let's call this OX module E. A vector bundle of the manifold X. The problem is that now we have a derivation that we didn't have before. So we have an extra piece of data, which is this guy is a derivation from O of X into E. So for the geometers, this should tell you that you have a map from omega 1 of this algebra OX into E. But you can forget about this. We have a derivation. So this means that del of AB is what? Del A times B plus B times L. What extra piece of information do we have? Oh, the bracket gives us some structure. So let's look at the bracket of B1. And here's where we gain information. The bracket of P1 with P1, so let me write that there. So the bracket P1 lambda P1 has two pieces, right? This is degree 1 plus 1 minus 1, which is the degree of the operation. It lands on P1. So the first part, I'll define it this way. This lives in P1. And then I have the linear term in lambda, and I'll define it this way. This lives in OX. Namely, if you look at the lambda bracket of two sections in E, of two elements in E, you have two coefficients for this lambda bracket. It's a polynomial, degree 1. This polynomial should be a linear polynomial. So I have two coefficients. The constant coefficient, I call it a pairing, and I get another piece of data. So this is this. And the constant term in lambda is a bracket. It's a bracket. So this is the data that I got. So now let's look at the actions. Okay? So this is the data, let's look at the actions.
Those are the bracket between P1 and P0.
Yes, but I was hoping no one would find out. Yes. So the bracket between P1 and P0 will give me an action. I'll force it in a second. Because the thing is that I have a derivation as well. So these two things should be combined. This bracket is not a Lie bracket, and we see immediately from skew symmetry of the lambda bracket that AB plus BA, right? The only thing that you pick up is del of here. This should be equal to del of AB. This guy is symmetric on the nose. Again, because it's skew symmetry. Oh, I have only 2 minutes. Okay. Let's continue. Let's look at this action of P1 on P2. Right? So I have del that goes from O into E, and then I can pair this with the bracket with any other section of E. So this gives me an action. Right? So I will declare that the action A F is equal to A del F is an action of E on O. And this by derivation. Okay, so let's start writing the invariants. This bracket satisfies the Leibniz rule. By the Jacobi condition of P1, A, B, C is equal to A, B, C plus B, A, C. So I have something like wants to be a Lie algebra, modulo the exact terms, satisfies the Jacobi condition. But I have a pairing, and now I want to check whether or not this pairing is invariant. I have this pairing on this Lie algebra, and I want to check if it satisfies some invariance condition. And for this, I need to check out the Leibniz rule. Okay? Okay, so let me finish. I'll just take 1 more minute. The invariance condition is as follows.
I mean, it's the first time I see speaker.
Yeah, I like to check my time. Yeah. It's a pity. I delayed, I don't know why. So let me see if I get this right. So let me just quickly check this. This is on del of BC. That's correct. So this should be the same thing as A BC plus B AC. So typically in invariant form this would be 0, but now we have something that fails to be 0 because of the exact term. Notice that this is the same thing as saying A acting on BC, on the function BC, because of this action here. All right. So finally, the last piece of information is essentially something that we don't need to write. I'll separate these two guys in a second, which is del F. This comes from taking the bracket of del F with something in A, and using the fact that a del inside goes out as a lambda outside. So del F lambda A, a bracket with A, is equal to 0. And finally, del F with del G is equal to 0. So these two actions, I'll leave them separate. So definition, if you give me a manifold X with ring of functions OX and a vector bundle E with this operation, which wants to be like a Lie bracket, is Q-symmetric, this is called a Dorfman bracket. Dorfman bracket. And satisfies the Leibniz rule. And these extra axioms. This is called a current Dorfman algebra. Dorfman algebra. I guess I'll leave the examples for tomorrow. But if the pairing, that's the thing. If the pairing here is non-degenerate, if this guy is non-degenerate, what happens? We have a map from omega 1 into E that came from the derivation. If that pairing is non-degenerate, we have also this map to this star. So, and this is an isomorphism. That's all I'm saying. And we always have this map to T. Well, I'm sorry, I always have this map to T because it acts by derivations. When this guy is non-degenerate, when that pairing is non-degenerate, this is called a current algebra. And this already appeared in the structure of T plus T star that Ricard was talking today with that adding this H. And, okay, so the statement is as follows. Poisson vertex algebras, generating degree 0 and 1, are current Dorfman algebras. If the pairing is non-degenerate, you get current algebras. And given any current algebra, of course, we construct the Poisson vertex algebra. I'll take the symmetric algebra, and let me just finish now, and I guess I'll leave all the examples for tomorrow. But the only comment I wanted to make is that I want to give one example of this thing, which is when X is just a point, or when OX is just a field. The only difference that we have from the previous time is that this guy survives. We have a Lie algebra. It's a Lie algebra. Oh, algebra. Because the Leibniz rule is satisfied, and this is Q-symmetric. There's no derivations. Just as in the original finite algebra, in the algebraic case over a point, I got a Lie algebra as well. But the thing that survives is the pairing from E tensor E to O, which is just a field. So we get not only a Lie algebra, we get an invariant bilinear form. That's it.
More questions?
Just the last one goes to K.
The last?
The G tensor G to K.
Oh yes, thank you. Yeah, the last minutes were very fast.
I have a question.
Yeah.
So if you try to change, I mean, the assignment of weights there, I mean, for bracket, etc., so what can you do and how much sense it would make?
Okay. Is Nick here? No. Okay, so
No, I mean, it's wrong. I don't know. Like,
do you want a physical statement or do you want a proper mathematical answer to that?
I want to hear meaningful physical statement, not in categorical language.
The statement is the following. If you want to have the Poisson bracket to have a degree different than -1, you are forced to look at the differential complexes and go into the right bracket. This is a statement. You might come up with a physical definition that I won't understand, but this is a theory. If you want to have a bracket of different degree than -1, you need to look in the derived setting. Actually, if Nick's claims is correct, then you're more than forced. I mean, this is There's an equivalence of categories between higher Poisson algebras and...
My question was much simple-minded. You change assignment and you go run through axioms, what do you get, right? For example, that's what I'm asking.
That's the thing, there's no examples. If you change the
but that's what physicists do, they do examples. I mean, I'm not asking for general statement which I don't understand. I'm asking, do you know any examples? Can you do it? Is it meaningful or not?
I'm telling you, no, you're forced to go into the right word if you want to have a bracket of different degrees.
Okay, then you didn't do examples, okay, but...
No examples.
Yeah, I just told you all examples. They're none.
Okay, that was my question.
Remember, when you get other kind of ground algebras, then the one you get here are exact ones.
No, that's not true. I didn't get exact current algebras. Let me think. I don't see. Okay, so this is going to sound like I'm going to contradict myself with Maxim's question. So first of all, I'm getting current orthogonal.
You just get all algebras.
Sorry?
You will get not necessarily exact, right?
Right. So this E could be anything that you want. In the case of the point, I already got an E algebra with an invariant paper. Certainly not exact.
So how do you characterize the anchor on
the anchor? So you mean the map from P into tau?
Yeah.
Well, I just have a Poisson, in my Poisson bracket, I have something, this lives in degree 1, and the lambda bracket with something in O should live in here. So this acts by derivation because of the Leibniz rule. So that's a map from P into T.
So Reutenberg worked out all this relation, so you can look at his paper and see how he defined, I mean, in purely algebraic setting, you define anchor and stuff like this.
I have to probably give you a more honest answer to your question. If you put the degree -1 here, instead of degree -1 as I did it, but cohomological degree -1, this is what is called the SUSY Poisson algebra. These are the supersymmetric versions. And in that particular case, you have examples. So degree -1, but then higher degrees -1 does not.
More questions? Okay, if there are no other questions, let's thank the speaker again. We will meet at 2:30.